Hello everyone. So for this lecture we'll be talking about Taylor and Maclaurin series as well as approximation using Taylor polynomials. So before we begin, let us recall Taylor's theorem, which states that if f has a power series representation about a number that is in the domain f, we denote the number a, then the derivatives of f of all degrees, that is for any derivative of f, exists, and furthermore f of x is actually equal to the series given by f raised to n of a all over n factorial times the difference of x minus a raised to the nth power, wherein our f raised to n is the nth derivative of f. And this works for all x in the interval of convergence of the series, wherein f raised to 0 is predefined to be our original function f. Okay, so we call the right hand side the Taylor series of f about a. And furthermore, whenever a is 0, this is called the Maclaurin series. Okay. So tip when solving for Taylor series, we usually will have to determine the derivative of f in hope to find a closed form or a pattern that defines our derivatives of f for easier solving. Now, another remark, it is sometimes true that a function is equal to its Taylor series at all points in the interval of convergence, but not always, of course. We will have to keep in mind of the counterexamples. So, before we proceed to any solving, let us recall a kth degree polynomial, kth degree Taylor polynomial, that is defined whenever f has the first k derivatives that are existing at a. And furthermore, the kth degree Taylor polynomial of f about a is defined by the series of f raised to n of a all over n factorial times the quantity x minus a raised to n from n equals 0 to n equals k. This is also denoted as the polynomial p sub k. So p sub k is the kth degree Taylor polynomial. Alright? Well, meanwhile, since we know that this function is not our actual Taylor polynomial, we can further define the remainder function as the difference of our original function f and our kth degree Taylor polynomial. And we usually denote the remainder function as r sub k of x. Alright? So remark, the kth degree Taylor polynomial is actually a very fast way of approximate values of f near our given value a. And furthermore, as k grows larger, the approximation gets better and better. But of course, the solving it takes gets more hassle and hassle. So tip, Taylor polynomial is still a polynomial. Therefore, we can actually multiply polynomials of a function to non-polynomial functions of a function to get a Taylor polynomial. So this will be demonstrated in our example problem. So let us consider this problem. We want to determine the Taylor series of y equals x squared times ln of 1 minus x about 0. We note that since it's about 0, this is also the Maclaurin series of our function. Okay, so let's begin. So we first evaluate the Taylor series of ln 1 minus x about 0. So by computing its first, second, third derivatives and so on, we actually get the following numbers. The first derivative of f is negative 1 over 1 minus x. The second derivative of f is negative 1 over 1 minus x squared. The third derivative of f is negative 2 over 1 minus x to the cube. Notice a pattern. Every time we take a derivative, the denominator grows by 1 degree. Meanwhile, the numerator grows by the current power. Therefore, by some pattern thinking, we get that our nth derivative of f is actually given by negative of n minus 1 factorial all over 1 minus x raised to n. Alright? So since Taylor series is about 0, we get that a is 0. So this allows us to substitute. So substituting our formula for Taylor series, we get that the Taylor series of ln 1 minus x is given by the series f raised to n of 0 all over n factorial times x raised to n from n equals 0 to infinity. However, we note that since we have a 0, computationally, it gives us the nth degree. The nth degree derivative of f is always negative of n minus 1 factorial. Therefore, furthermore, a substitution of f of 0 yields 0. Thus, the Taylor series of ln 1 minus x is given as follows. It is the series of negative x raised to n all over n from n equals 1 to infinity. So why is 0 not included here? Because our f of 0 is 0. Therefore, it's removed already. And since we can multiply a polynomial to a Taylor series and still yields a Taylor series, we can multiply x squared. Since it's a polynomial, it gives us the actual Taylor series of our function, which is the negative of the summation x raised to n plus 2 all over n from n equals 1 to infinity. This is our Taylor series for our given function. Alright, so our second problem, we want to compute the fourth degree Maclaurin polynomial of g, and we want to approximate g. Now our g is given by x times e raised to 2x. First, we note that to get the Maclaurin polynomial, we recall that a is 0 in a Maclaurin series or Maclaurin polynomial. Therefore, we have our given formula as follows, which is f raised to n, the nth degree derivative of 0 all over n factorial times x raised to n, starting from n equals 0 and to k. So first, we compute the Maclaurin polynomial of e raised to 2x, since x is a polynomial, particularly linear function. So upon computation, we get that f raised to n of x is given as 2 raised to n times e to the 2x. This can be computed by brute force. Since it's just up to the fourth degree, we can just take the derivative 4 times and we'll still get the same result. Therefore, the Maclaurin polynomial of f is given by f of x is equal to the series of 2 raised to n over n factorial times x raised to n from n equals 0 to infinity. So upon taking the nth degree polynomial, the nth degree Maclaurin polynomial, we just substitute k equals 4. And moreover, since g of x, our given g is just x times f of x, we can just simplify and multiply x to the entire series. So take note of the tip we discussed earlier. We can also take up until the fourth derivative and we will still get the same result. Therefore, by subsequently substituting into the series, we get that g of x can be approximated by the following series: the summation of 2 raised to n over n factorial times x raised to n plus 1 from n equals 0 to 4. Or, when expanded, we get our following result. x plus 2x squared plus 2x cubed plus 4 over 3 x to the 4th plus 2 over 3 x to the 5th. And this is our answer for part A. Alright, so to get part B, we just substitute in whatever x we want to substitute. So since we have our given g of 0.3, we just simply substitute 0.3 into our given function. Therefore, upon computation, we get that g of 0.3 is approximately 0.54642. And that is our final answer for 2B. So that's it for Taylor and Maclaurin series. Hope you learned something. And thank you.